Geotrig Lesson 6. This is on solving fractional equations first. So we got a lot of information here before we even start the problem. But as you can see here, this is what we're going to call a fractional equation. It's got fractions and there's an equal sign. So what we're going to do is we're going to be able to solve these. And to do that, we're going to work on the premise of I don't like fractions, and you guys probably don't like fractions, and so we're going to fraction bust. We're going to get rid of those fractions. Now, in the last lesson, we talked about complex fractions, and we could easily deal with the complex fractions by finding the LCD and multiplying the top and bottom of the fraction, the big fraction, by that LCD. So today we're going to do the same thing. We're going to find the LCD, and then we're going to use that LCD to get rid of denominators again. So I took the liberty of writing out the steps here. We have finding the LCD. First of all, remember, we're factoring all of our denominators. So we factor all those denominators. And remember, it's kind of like a potluck party of bringing things to the party. And we are going to write down the first denominator in its completeness. And then we start to multiply anything that's missing or extras, repeated extras. So remember, if the first guy brings an x, the next guy can't bring x, but he can bring x squared, which means he can bring that extra x. So we add the extra or multiply the extra x into the LCD. So remember, we have to use LCD because look over here at solving fractional equations. The first step to solve a fractional equation, this thing, is find the LCD. So I'm going to go over here and I'm going to factor all of them out. Start with 7. Is an x plus 2 a 7? No, so I multiply it in and do the same thing with 3. We'll get to that when we do our problem. Then I'm going to use that LCD by multiplying both sides by the LCD. So multiplying both sides by the LCD, I am going to be able to cancel out my denominators. We're going to simplify anything that I have to, put numbers together that you have multiplied, and then we can start to solve for the variable in question. So, here we go. We are working on our problem. Now, the first step again was to factor all of the denominators, and as you can see, 7, you can't break it down. X plus 2 you can't break down because it's a plus sign. You can't factor anything out. You can't take a 2. You can't take an x. It's x plus 2 and 3. So to find the LCD, I'm going to go over here and put LCD. And I write down the first one, 7. The guy shows up with a 7, he's in. The next guy wants to bring an x plus 2. Since x plus 2 is not 7, that we know of, so we can put it in. And the last guy gets to bring his 3. Make sure that you leave it separated but yet multiplied. We do not want you to make that a 21 times the quantity of x plus 2, which you can, if it works, fine. Or, even better yet, do not multiply or distribute the 7 and 3 in, because you're going to want to use them in this form to be able to cancel. Now, notice on the second step it said multiply both sides by the LCD. What's really happening is that I am going to put parentheses here, and I'm going to put LCD and the LCD. Now, I'm not doing it right now. I will put numbers in there in a second. I'm using LCD for the reason because I have to multiply these two. And then, because there's a group on this side, I would have to distribute. But if that's the case, that means I am actually multiplying every piece by the LCD. So, in other words, instead of saying, hey, multiply both sides, maybe go back to those steps and say, multiply everything by the LCD. So now here we go. I'm going to multiply it by 7, x plus 2 and 3. Over here is 7 times x plus 2 and 3. 7 x plus 2 and 3. I'm multiplying everything. And the cool thing about it is because 7 and the 7, when you divide them, they cancel. They go to 1. X plus 2 and x plus 2 cancel. And 3 and 3 will cancel. So what I'm left with is x plus 2, a 4, and a 3. plus a 3 times a 7 times a 3 equals a 5 times 7 times x plus 2. So now at this point, this is where I said simplify it. Because we know what 4 times 3 is. 4 times 3 is a 12, and now I can take the 12 and bring it in. That's 12x plus 24. 3 times 7 times 3, that'd be 63. And 5 times 7 is a 35, and 35x plus 70. Now that looks a lot like a regular, like algebra 1. Whoops, sorry, I forgot an x on that 35. 30 is an algebra 1 or algebra 2 style problem. Variables on both sides. I guess we could simplify this up just one more step, and that would be, what, 87? If I put those two together. So 35x plus 70. So now I'm going to move 12x, start to put this together, and minus 70, so 17 equals 23x divided by 23. X is equal to 17 over 23, and you are done. Now, you guys hopefully, knowing that we're in our 6th lesson of this book, that it's okay to have decimals, it's okay to have fractions. Because this is a fraction, and it's a nice fraction in a way, we're going to leave it there. You could convert that to a decimal if you wanted. Now, look at this. If I want to know if I'm right, I'm going to actually check it into the original problem. I'm going to put 17 over 23 in for x, add it by 2, divide it into 3, add it to 4 sevenths, and I should get 5/3. So I'll let you guys do that on your own. But here's another thing too, is that x is on the bottom. It's actually x plus 2 on the bottom. There is some value that you cannot be. That value corresponds to the fact that you cannot divide by 0. So I know by just looking at this, x plus 2 can never equal 0, or x can never equal negative 2. But since this number is not negative 2, I'm okay with that. The answer is 17 over 23. And that's how you would do those problems. Multiply by the LCD, simplify, gather up like terms, and solve for the variable that's in question. So the next problem is this. It's 3/7 x plus 2 over 5y equals 11, and 0.03x minus 0.2y equals negative 0.37. Each one of those individually is what we just had to handle. But unfortunately, there are how many variables in it? 2. And the only way that you're allowed to solve for x and a y, or 2 different variables, is if you have 2 equations. This is a system. So what we did technically to get rid of fractions over on the other problem once, you have to do twice, and then you're left with a system that you have to solve. Okay, so there's a couple different things. First off, before we even get into fixing this, overall, we have to be okay with looking at something like this. That's a normal system that you guys, I guess we call normal, right? Yeah. You guys have seen that. You've dealt with that in Algebra 1. You've dealt with it in Algebra 2. And we're still dealing with it today. There are some things you guys should know about this. There are 3 solid plans of action to solve these. What are those 3 ways? Joe?
Elimination.
Elimination's one of them. Yeah. Substitution, third one. I was actually surprised last hour got this real quick. Substitution, elimination, and the one that really doesn't always work the best for us. Graphing. Yes. If all of them we would choose, graphing's probably not our first option. Because we don't make perfect looking graphs. But the algebraic ways of substitution and elimination always work, yeah? So, we have to be okay with elimination, which means getting rid of one of the variables by adding or subtracting the equations. Substitution is where you solve for one variable and you kick it into the other equation and solve. Okay. We can go over some of those processes. We will go over at least one of them today when we solve the top one. But there are 3 different outcomes to solving a system. What are those? One solution. They will cross another one. Not 2 solutions. Infinite many solutions because they end up being the same line. And the last one, no solution because they end up being parallel. So you have to be ready for all of those. Now wait a minute. So same solution would be, if I can change colors here, you can't even hardly see the difference, right? Because you shouldn't be able to. It's one line on top of the other. If they cross, you got one solution. Now, how does it look in the algebra side of things? Because if I graph them, I can see that really easily. But if I don't graph it, how do I tell, using algebra, there's one solution, no solution, or infinite many? Infinite many is the same equation, but what is your answer then? When you get down to it, you start solving.
Oh, like if you plug in any number.
Any number will work.
Yeah.
Okay. Not necessarily. It has to follow the same pattern as an x and y.
Right.
So it's not like there's anything will work, just that there are an infinite many solutions. Okay, let's start off with this one here. If there was a solution, you eventually would get x and plug it back in and get a y. You would have a point, right? Do we still get that same result when there is, when there is no solution? What happens? What do you get down to the bottom of all your solving? What does it look like?
They do not line.
Yeah,
They do not line up. How?
If you plug it back in, it doesn't equal the number.
Doesn't equal the number when you plug it back in. Not quite. That just means that it could not be a solution at all to the solution. Doesn't mean that there are no solutions.
it'd be like 20 equals 10.
There we go. 20 equals 10. Is that true?
No.
Remember, if you get down to the point where you eliminate all of your variables and 20 equals 10, that can't happen. 0 equals 5. Can that happen? Is that true?
Not really.
No. So that means no solution. What about infinite many then? Same number. 5 equals 5. How about x equals x? Will that also? Yeah. Because technically if I subtract x from both sides, I get 0 equals 0. If I divide both sides by x, I get 1 equals 1. And that's always, always true. So infinite many, no solution. And if you get an x or a y value, you plug it back in to solve for the other. Any questions on that? That's all background information that you guys are going to need to know to solve it after we make it look pretty, right? We got to fix those though. So give me a second here. Okay, here we go. Well, first of all, you guys have already admitted you guys don't like working with fractions. Would the second question be, do you guys like working with decimals?
No.
Not necessarily. More of us would be comfortable with that though than they would be fractions. But let's deal with the top equation. Do you guys notice that the top equation is really just 3 different fractions?
Yeah.
And didn't our last problem have 3 different fractions and an equal sign?
Yeah.
If I found the LCD of that and multiplied it to all of them, wouldn't it just cancel?
Yeah.
So yes, when you're dealing, it's a rational function. So therefore, we still can deal with it the same way. What number does 7, 5, and 1 all go into? What's that?
35.
35. 35 is the LCD. Now the question, could I use 70 as well?
Yeah.
It's a lot more work though.
It's a lot more work, but does 7 go into 70?
Yeah.
Does 5 go into 70? And 1?
Yeah.
So it would work if I multiply both sides by 70. It would cancel the denominators. But it would make larger numbers in the numerator, and I would like to avoid it if possible. But if you're ever stuck and you know that, hey, 70 is a multiple of them, then use it, please. I'd rather have you cancel out denominators than not. So, using the same idea we just did in the last problem, could I put a 35 here, a 35 there, and a 35 there?
Yes.
And so now I can start to cancel. What's 35 times 3? Divided by 7. Or, could I think of it the other way? Could I say, hey, what's 35 divided by 7? 5. And multiply that by 3?
15.
Oh, that's 15. That's easier. That's 15x. What's 35 divided by 5? Times 2. So it's plus 14y. And this one is interesting. What's 35 times 11? Or could I take 11 and make it this? Is 11 10 plus 1? No calculators. What's 10 times 35? 350.
50.
What's 1 times 35?
351.
35. And what's 350 plus 35? Right? Because if I distribute,
Oh, yeah.
it's 385. I didn't need a calculator. I used the distributive property to my advantage. I think that's pretty cool. Does everybody understand how I got those numbers? If I had a calculator, I may have just done 35 times 3 divided by 7. I'll still get 15. Now we fixed 1. That's nice numbers. Some of them are kind of getting large, but that's okay. What about the 0.03? 3 hundredths.
I'm sorry, I think it's a 385.
So, do you guys remember back to this magical number? It was really magical. That when you multiplied or divided by this magical number, decimals went whoop, whoop, whoop,
10,
whoop, whoop, whoop.
100, or 1,000.
There you go.
10.
It was 10, 100, and 1,000, and 10,000, basically powers of 10. If you multiply by 10, the decimal place went to the right. If you divide by 10, it went to the... I want those decimals to go which way?
Right.
To the right. Now,
10.
the rule of thumb is the number of zeros you need after your 1. So is it a 1 0? Is it a 10? 2 zeros would be 100. 3 zeros would be 1,000. Determined by the most amount of zeros or decimal places you have to move. So if I was here, I'd go 1, 2. Because after the 3, it becomes 3, right? Here it becomes a 2. That's only moved it once. This one has to be 1, 2. You used the biggest one. The biggest movement would take 2 moves. So I'm going to multiply both sides by 100. And if I multiply by 100, I'll get 3x, yes?
Yeah.
Yeah.
Minus 20y. Because, look what happens. I have an extra loop that has to have a 0 then. And equals a negative 37. Not too bad, right?
Nope.
Okay. Now we need to solve it. Now it looks more like a traditional system.
Correct.
I personally think we should use elimination.
Same.
Remember, in elimination, you try to get the x's or the y's to have the same number but opposite in sign. What do you think is going to be easier? Getting 15 and 3 to be the same or 14 and 20?
15 and 3.
I think 15 and 3 as well. What number do do you think you can multiply to that second equation to make that happen?
3.
Negative 5. Now, make sure you are distributing all the way through. That becomes negative 15y plus, that is an x, sorry, x plus 100y equals all the way across a positive what?
Yeah.
185? And then what do I do with that top equation and the bottom one? Not subtract. One's positive, one's negative. I'm going to add because I engineered, guys, the 15x and the negative 15x to disappear. 114y equals 570.
Correct.
And then to get y by itself, you're just going to divide by 114. So it ends up equaling 5. Are we done? No, but guess what? This one lends itself, that means it lends itself to more of the thinking that this has how many solutions?
2.
One.
1.
There's only one, none, or infinite many. So we got an all y value. More than likely, there's also going to be a x value. And how do I find that x value?
Plug the line.
Plug it in. Do you guys really want to plug it into one of those?
No.
No.
Plug it in.
I'm going to plug it into one of these blue ones. Which one? Top one? Really?
No.
I'm going to go with the bottom one.
No, top one.
I don't like the top one because it's got really big numbers.
Wait, but can't you just...
You can use any of those choices. So 3x minus 100 equals negative 37. Add 100. I'm moving kind of fast because this is all solving. It's algebra. 3x equals 63. And divide by 3. X is equal to 21. Now you're done.
Or are you?
But really, if it's a point, you probably should set it up as a point. So it should be 21, 5. Okay, the last problem that we're going to do today. The last problem is radical equations. And you're going to have to always check for extraneous solutions, guys. These are the problems because we're squaring and square rooting and all of those things. Extra solutions start getting slipped into the answer key. And so you always, always, always have to make sure that they work. Okay, I put the steps in there. Solving radical equations. Number 1, I want you to separate the radical. That's a cubed root, square root, fourth root, fifth root, stuff like that. Separate them from all else. There's a side note to that. If more than one radical is present, you need to put 1 on each side of the equal sign.
Okay. Why?
Because you're going to try to undo both of them at the same time. 2, you apply the correct power to cancel the radical on each side. Here's the thing. How do I get rid of a square root of x? How do I get rid of a square? Or square root, sorry. I square it, right?
Yes.
How do I get rid of a cubed root?
You
You cube it, because those are inverses. They're opposites, right?
Yeah.
So if you're dealing with a problem with square roots, you square both sides. If you're dealing with cube roots, you will cube both sides. Now, unfortunately, this one has a side step as well. It says, if we separate them to each side, more than likely, you won't be able to cancel both at the exact same time. You will have one of them left over. So then you repeat steps 1 and 2 by separating and getting rid of the power. So you may have to take the power of something twice. Hence, you start to add more extra solutions. You're making it a larger power than what it really should be. And then, once you get rid of all your radicals in step 3, you can solve for the variable. It's not too difficult. Take it one step at a time. Write everything down. Okay, now we're into this problem. I've got the cubed root of an x minus 5 minus 2 equals 2. Step number 1 said, isolate, right? Separate. What do I have to get rid of then?
Just radical.
No, I can't do that yet.
Oh, the 2.
I gotta get rid of the minus 2. To get rid of a minus 2,
Add 2.
everybody with me, right?
Why did we write down all the stuff on the erase?
So is everybody okay by adding 2 to both sides? I got a 4.
Yes.
Now, from here, the radical is by itself. That is a cubed root. So to get rid of a cubed root, I will take it to the third part. But what I do to the left side, I have to do to the
Right side.
okay? Cubed and cubed root will cancel.
X minus 5
Equals 4 to the third part. X minus 5 equals, what's 4 to the third power?
32.
60 times 4.
No, that's wrong.
4 times 4 is 16 times 4.
That's 64.
Six-
Yeah, Marty.
64?
Actually?
Yes.
Yes.
Add 5. Okay. Now, we end up getting x equals 69. Now, what we need to do is make sure that this is the correct answer. So, thinking about it, what's 69 minus 5?
64.
And what's the cubed root of 64? It's 4. And what's 4 minus 2?
That's 2.
2. It's check. We're good.
69.
Lesson 6, day 2's homework's on page 53. This is 5 through 8. 5 through 8 is like the first problem, or 5 through 7 is the first problem. 8 is the only one that deals with this radical stuff. I did not include the system problem because we'll do more on systems in the next day, so therefore I'll assign that on the next day. Have a great day.